Hello friends, in my this video I am going to discuss about the circuit of current regulation by feedback. Okay, so let us start. A voltage regulator provides a constant DC output. Okay, you all know about voltage regulator. Suppose this is one varying load. RL. Okay, then you want a constant voltage drop across the varying load. Then what you do, you connect one Zener diode in reverse bias in parallel with this load. Then what will happen, we know that in reverse bias the Zener diode acts like a voltage regulator. So in reverse bias, suppose it is given that what amount of DC voltage the Zener diode will produce at a reverse bias in breakdown region. Suppose this is in specification sheet, it is given as Vz. Now although the load resistance will vary, but because of the application of the Zener diode in reverse bias, always across the RL resistor the voltage will maintain as Vz, and this voltage depends on the what type of Zener diode we are using. Different Zener diodes have different Vz, and that depends on the Zener diode. We can get this data from the specification sheet. Okay, like if for every diode there are specification sheets. Like for BJT you have done several experiments in lab, then there you have used the specification sheet. Like that, from the specification sheet we get this information. Now here by Zener diode we can regulate the voltage, so that this is the special purpose application of the Zener diode, that we can in reverse bias Zener diode acts like a voltage regulator. But how can we regulate current? Let us discuss. So in some application we may require constant current, okay, across a varying load. Okay, so the circuit that gives a constant DC current irrespective of the load resistance is referred as a current regulator. Okay, like Zener diode is voltage regulator because it maintains a constant DC voltage across varying load resistor RL. Okay, similarly the current regulator circuit, what is the working principle? It maintains a constant current across a varying load resistor. See here, suppose this is one resistor and which is varying, and suppose the resistor is RL, and suppose the voltage across the RL resistor is V. Now suppose the RL decreases, then the current flowing through the RL will increase, and suppose the RL increases, then the current flowing through the resistor will decrease, because we know V is equal to IR. So obviously when V, that is voltage across the resistor, that is this voltage is constant, then obviously I proportional to 1 by R, that is inverse relation, so that when the resistance increases current decreases, and when the resistance decreases current increases. But suppose if the voltage across the RL is constant and the RL is varying, then also we want a constant current flowing through this circuit. Then what we can do, we can implement one circuit, okay, that is called current regulator circuit, that we will discuss. But before going to that, I will just explain or give a quick recap on three basic funda, whatever you know from the transistor analysis. This is one PNP transistor and this is in forward active mode. See here, the P-type emitter is connected with the positive terminal of the battery VBE, and the N-type base is connected with the negative terminal of the battery of VBE. So that basically this PN junction, this emitter base junction is in forward bias. And see the base collector junction, N-type base is connected with the positive terminal of the battery, and N-type base is connected with the positive terminal of the battery, and P-type collector is connected with the negative terminal of the battery. So basically this base collector junction is in reverse bias. So as the emitter base junction is in forward bias and base collector junction is in reverse bias, so obviously this PNP type transistor is in forward active mode of operation. And the current versus the collector current versus the base emitter voltage relationship for the PNP type transistor is IC equal to IS into e to the power VEB by VT. And for NPN, what is the relation? Same relation, but you have to write here VBE, because for NPN the relation is IC equal to IS into e to the power VBE by VT. But here the relation is IC equal to IS into e to the power VEB by VT. Clear? This thing you all know. And this is very important relation. As we know, IC equal to IE equal to, that is emitter current equal to IB plus IC, and we know IB equal to IC by beta. So that the relationship between emitter current and collector current is IE equal to IC by beta plus IC. So that emitter current is dependent on collector current. If the collector current increases, emitter current increases. If the collector current decreases, emitter current decreases. This is clear from this expression. Now, with the three basic information, we are ready to analyze the circuit which can regulate the current. Let us check. This is the circuit which can regulate the current. This is the load resistor RL, and through which IL current is flowing. Suppose the load resistor, due to some external reason, what happens, due to temperature increase or some reason, what happens, the load resistor changes. Okay, but what happens, across the load resistor the voltage is constant. So that to avoid the change of IL, we can implement this circuit configuration. What is this? Let us check. See, here we are giving, in this terminal we are giving the V in, that is input voltage. Clear? And here R1 and R2 are two resistors which are connected in series. And see, this is one PNP type transistor, because emitter current is in this direction, in the entering in the device. So obviously this is one PNP transistor, because see here the IE in PNP type transistor enters in the device. So obviously this is one PNP type transistor which is named as T, and across the emitter base the voltage is VEB. Emitter is positively connected with the positive terminal of the battery, and base is connected with the negative terminal of the battery. See here this biasing. So that's what I have denoted here by plus and here by minus. And this is another resistor, suppose let us assume as R3. Okay, and this is what? This is Zener diode. Now we will apply the Zener diode as voltage regulator. So obviously we have to connect the Zener diode in reverse bias. So is it in reverse bias? Yes. See, in PNP type transistor, this is operating in active mode. So base, for emitter base junction, base is connected with the negative terminal of the battery. See here, the base is connected with the negative terminal of the VBE, and see, with the base the Zener diode is connected. So obviously the P type portion of the Zener diode is connected with the negative terminal. Obviously, so N type will connect with the positive terminal, that is C, it is connected with the emitter, and the emitter is connected with the positive terminal for biasing case. Okay, so basically the Zener diode is in reverse bias. Okay, so obviously it can act like a voltage regulator. So we have assumed a constant voltage drop across the Zener diode, and that is Vz. And here, for safety purpose, we can use one potentiometer. Instead of R2 resistor, we can tune the resistor, or we can control the resistor. So we have just denoted by potentiometer, but you can use R2 resistor, that is one fixed resistor also, no problem. Now how this circuit works? Okay, suppose due to some reason IL, that is the load current flowing through the varying resistor RL changes. Now what is IL? IL is basically collector current for this transistor T. See here, the emitter current is entering and base current is coming in this terminal, and collector current is going out of this circuit, because for PNP, see, the base current and collector current comes out of the circuit and the emitter current enters. Similarly, same thing is happening here. So basically IL is the collector current. Okay, now suppose what happens, suppose IL increases, so collector current will increase, and just I mentioned, see this relationship, that if collector current increases, obviously emitter current will increase. So obviously, as emitter current means the current flowing through this part will increase, So obviously the current is basically flowing through this R1 R2 series combination. So obviously as the current flowing through the series combination of R1 R2 increases, so obviously the V1 will increase, because V is equal to IR. Here V1 is equal to R1 plus R2 into IE, where I is the emitter current which is passing through the transistor T. So obviously if the emitter current increases, V1 will increase, and if you apply KVL in this loop, you will get VZ minus VZ plus V1 plus VEB equal to 0. Clear? So obviously what we can get, that VEB equal to VZ minus V1, general voltage which is a constant, minus V1 voltage which is the voltage drop across the R1 and R2 combination. Now as the emitter current increases due to increase in IL, V1 increases. So as V1 increases and VZ is constant, so obviously VEB will decrease, and we know that the collector current for PNP transistor is IC equal to IS into e to the power VEB by VT. So as VEB decreases due to increase in V1, so obviously IC, that is collector current, which is IL, that will decrease. So basically what is happening, if suppose RL decreases, then IL will increase. So as IL increases, IE will increase. So as IE increases, V1 will increase, and as V1 increases, VEB will decrease, and as the IL or IC is proportional to the exponential factor with VEB, so obviously as VEB decreases, IL will decrease. So when the current want to increase, the VEB decreases in such a way that the current will decrease and maintain its previous value. So in this way, this circuit gives us a constant DC current as output in the varying load resistor RL. Okay, so this is called current regulator circuit. So by application of Zener diode with the feedback, we can get a current regulation. If we want constant current in some application, we can use this circuit. So I hope the analysis of the circuit is clear to you. Just very important concept is that due to change in resistance, the IL will not change for this circuit. Okay, this is all for this video. In my next video, I will show you some more concepts. So basically this is an application of feedback. The increase in IL is fed back to the input circuit, and the input is decreased in such a way that the IL decreases. So this is one application of negative feedback, because of the increase in output, the input is adjusted and it is decreased. So it is subtracted, and subtraction is done in negative feedback. So this is one very important application in negative feedback. Okay, this is all for this video. Thank you for watching.